For centuries, scientists did their best to gain accurate and precise knowledge about the natural world. But did you know that there's a limit to our certainty about some properties of objects? Let's find out.
Heisenberg Uncertainty Principle was developed in 1927 by German physicist and quantum mechanics pioneer Werner Heisenberg. It states that you cannot know the exact position and momentum of an object at the same time, and is represented by this equation. Well, don't worry, we'll break this down. The uncertainty in position times the uncertainty in momentum is greater than or equal to Planck's constant over 4 pi. This means that delta x is inversely proportional to delta p. If one increases, the other decreases. So if we are certain about the position of an object, then we are highly uncertain about its momentum, and vice versa. To understand how this works, we need to dig deeper into the wave-particle duality of matter, which tells us that all matter has both particle-like and wave-like behavior. In nature, we can see examples of particles that have a definite position. We can also see waves, such as ripples on the surface of water, but they don't have a definite position. So let's imagine something that has properties of both. A wave packet. A wave packet is the sum of many waves having different momenta. Yes, waves have momentum related to their wavelength. Going back to our wave packet, can we know its position? No, but it has a range of possibilities. Did you know that the more waves we add, the more confined the wave packet will be? In other words, increasing the possibilities in momentum decreases the possibilities in position. This is also true the other way around, just as the principle says. But why can we precisely know both momentum and position of the objects that we can see? Does this mean that this principle doesn't apply to large objects? Actually, this principle applies to everything, including large objects. Let's say we're going to confine a basketball to within a millimeter. This will give us a very small uncertainty in momentum. Recalling the definition of momentum in Newtonian mechanics and knowing the mass of a basketball, we will find out that the velocity of the basketball would be somewhere between 0 and 10 to the negative 31st meters per second. Wow, that's very slow. This is why we can easily disregard the effects of quantum principles in real life. But this principle is important in small objects, such as subatomic particles. In fact, it is the reason why we can only use orbitals, a range of possibilities to represent an electron's position in an atom. Welcome to the weird world of quantum mechanics, a branch of physics where everything might seem weird and intimidating, but also interesting.